Thank you, Taylor. So just give a minute for everybody to click on the right button, and we will start. So, good morning. My name is Emmett Fletcher from ESA's Communications Department. Today with me is also Taylor Willis from the Communications Department, and Taylor is the one who's actually running this, to be perfectly transparent with everybody. So today we have a very fascinating subject, which is the Proba-3 launch and the Proba-3 mission. And today to discuss this with us all is the Director of Technology for the European Space Agency, Dietmar Pilz. We have the Proba Project Manager for ESA, Damian Galano. Diego Rodriguez from CERN, who's the Space Director at CERN. And the mission scientist for Proba, Joe Zender, also from the European Space Agency. So without further ado, what we'd like to do is play a very short video to give an overview of the mission itself. And after that, we will go into a very concise presentation about the Proba mission and the interesting aspects around it. So I think if that's okay, Taylor, if we could play the video, and then we will start the meeting, let's say. Thank you.
Don't have any sound on my side.
Same for me. I have no sound.
Yep.
Taylor, we had the same issue with the media briefing just before in French.
Okay.
Maybe what I can do, I can share my screen and share the video in a different way. It worked for the.
Okay, that would be perfect. Thank you very much, Damien.
Let's try this way. Yeah,
experience is 100%. Thank you so much, Damien.
I learned something from the previous session, so let's try.
Proba-3 equals two spacecraft flying together in pursuit of one common goal.
Proba-3 is going to emulate the principle of a total solar eclipse, because what Proba-3 wants to do is to study the outer part of the sun's atmosphere, so the solar corona. The problem is that for studying it, we need a total solar eclipse, and these only happen a few times a year, and they are very brief. So Proba-3 will emulate a total solar eclipse on demand.
One spacecraft will cast a shadow onto another, just as the moon does to Earth during a solar eclipse.
In the very beginning, still like 20 years ago, when I first time heard about Proba-3, I said, wow, this is really something to be done.
Moving at kilometers per second, the pair need to hold position precisely, down to the width of a fingernail.
Proba-3 is exactly the kind of mission where ESA excels. It applies advanced technology to gather new science while trying out a wholly novel way of operating in space.
To develop a number of new technologies, a number of new sensors, so each spacecraft knows where the other one is.
Like self-driving cars, the spacecraft steers autonomously, harnessing radio and laser links, LED tracking cameras, and shadow sensors.
In the end, the proof that our technology works well will be in the quality of the data, opening a window onto a crucial part of the solar system that is usually hidden from us. I'm proud of how ESA has worked with European and Canadian space companies to make this mission possible, and I wish the Proba-3 team the very best of luck.
That's great. Thank you so much. Experience shows. Thank you. Okay, so what we'd like to do now, Damien, if you could start the PowerPoint, and I will pass the floor once it's up to Dietmar Pilz, who is the Director of Technology for the European Space Agency.
Yes, thank you very much, Emmett. I hope you can all hear me well. Indeed, my name is Dietmar Pilz. I am leading the Directorate of Technology, Engineering, Quality here at ESA. I'm right now joining you from ESTEC, the site where also most of my team is located, and myself. And where we have managed, projected, engineered, designed from for the ESA part, the Proba-3, of course, and we will see this later with our industrial partners, and particularly on Senair and Redwire, as we will produce and introduce later. So my directorate is usually known for the technology, for the competences, for providing these competences to all of our projects, also for making sure that the quality is in line of what we can expect and what we should expect from these fantastic missions. But we are also having one area which we call in-orbit demonstration and in-orbit verification, where we are verifying, where we are testing, checking out new technologies, and or where we are providing also possibility to our partners, to industry, to test and to verify their technologies on board of some of our platforms. So within that area, since quite a while, we have an area which we call Proba, according to the Latin name of being try it, test it, check it out. And that's what we want to do with this kind of fleet, or with this kind of initiatives on Proba. Proba-3 is one of the most exciting satellites that we develop within this in-orbit demonstration of new technologies. We fund this under the General Technology Program of ESA, the so-called GSDP program. And of course, since this has a huge scientific relevance here, we're not only testing here formation flying, we're not only improving our knowledge and competences in this part. No, we are actually using this for a high need in the science community, obviously to study and research the corona of our sun, of our solar system, and therefore, of course, we work here very close and with and under the Science Directorate as a so-called mission of opportunity. But besides that scientific objective, Proba-3 is there to demonstrate really precise, accurate formation flying. So, I mean, in simple words, and you can already see this at the director level, I'm doing the very simple presentation here, and then I will hand over to the more complex part to Damien, who is leading the project. So, what do we think? What is about formation flying? We have here a simple symbolic picture of several airplanes that you can see in some of these air shows. And in principle, that's also what we want to show in Proba-3. Next slide. And why? So if we would be able to have several satellites close to each other in an absolute accurate, precise formation, we would actually be able to assemble, so to say, larger instruments that, of course, then are composed out of several satellites. And we could use this in order to look even further, to compose sensors that are able to look even further in astronomy, in exoplanet detection and their characterization. Here, obviously, also for solar system science, climate change, with the idea of bringing together several satellites, being close and acting as one instrument. That's the overall idea of this formation flying here. And we cannot do this in one instrument. I mean, we all know that the launchers have been increasing in their power and in masses that they can bring into space. But no matter what you do, there's always a limit. So we want to find ways of increasing the size, and this composition, this flying in a very accurate way, is exactly what we want to demonstrate here. And therefore, we chose Proba-3 for these two reasons: improve our knowledge and our competence technology for this very, very exact and precise formation flying. And then, of course, use this immediately for science and demonstrate new enabling mission concepts. So that's maybe as a first introduction about the overall concept and about Proba. And with this, I would hand over to you, Damien. And by the way, I liked your video with the little hairnet before. Very nice. So Damien, yours.
Thank you. Thank you very much, Dietmar. So I am Damien Galano, the project manager at ESA for this Proba-3 mission. I joined the project in 2014. So you can imagine that I know very well the ins and outs of this mission, and very excited for the time to come, the launch and the realization of this mission after all these years of effort. So as it was already introduced in the video, the demonstration of formation flying, we want to do it by delivering unique science in the field of study of the sun corona. The sun corona, the atmosphere that is around the sun, is not visible except when we have a total solar eclipse, when the moon, which is a very large object, block the light from the sun, create a shadow, and if you are in this shadow cast by the moon, you can see the corona sun. It's been already dozens of years that we have invented specialized scientific instruments that are called coronagraph. They produce the same principle. So instruments that are made of specialized optics with some occulting disk to block the light from the sun and be able to see the corona. You see at the bottom a picture from a coronagraph that is flying on the ESA mission SOHO. It's working well, but the size of this coronagraph is typically 1-2 meter long. And what we want to achieve with Proba-3 basically is to create a giant coronagraph made of two pieces or made of two satellites. The first satellite is the occulter satellite or occulter spacecraft that accommodates a circular occulting disk of 1.4 meters in diameter. This disk will cast a shadow, and the other spacecraft, the coronagraph spacecraft, embarks a telescope, and this spacecraft must be positioned precisely such that the telescope is in the center of the shadow cast by the occulter at a distance of about 150 meters. And this is where formation flying comes into play, to have this capability to control and maintain the relative position of the two spacecraft very accurately in a very stable way. And the accuracy we are after is in the millimetric range. So from a, let's say, technical point of view, this is what Proba-3 is in a nutshell. It's an experiment in space to demonstrate a new concept, a new technology that is technically challenging. But I think the price, let's say, you have to pay if you set yourself ambitious goals, and on Proba-3 we have ambitious goals. So very challenging because we need to control very well the flight path of the two spacecraft, and to achieve this, we had to develop many special technologies and equipment specifically for the mission. So that was my part. I now hand over to Diego.
Okay, I hope you can hear me. I'm Diego Rodriguez. I'm the head of the Space and Science Department here at CENER. CENER, at the prime of this mission, a quite challenging mission and duty for us. Well, now you can see here the orbit. This is the orbit is quite very eccentric. The reason is that to perform formation flying, we wanted to have a quiet environment where the speed of the satellites was lower. So in every period and the time in every orbit, and the time is around 20 hours, we have a region in the left you see in green. In that area, the satellites free fly. They follow the orbit in a natural way. As we approach to the apogee, which by the way is very far from the Earth, around 60,000 kilometers, then and after commissioning, the two satellites will be able to, in a fully autonomous way, to start first making the acquisition and then finally fly in tight formation. When we are in that apogee, at, as I said, 60,000 kilometers, they will maintain then the formation, this almost 150 meters with this precision of millimeters, and then we start the science. And then the coronagraph will start looking to the sun, to the corona of the sun. We benefit of 6 hours of observation, which is obviously much more of what you can do during a natural eclipse. After that, we go back and in the left side of the orbit, in the perigee, which we get very close to the Earth, to almost 600 kilometers. As I said before, the formation is loose. And then we repeat the orbit again. Okay, next. Okay, you have here all the participants, the list of participants to this mission, which has involved many companies, more than 40 companies, across 14 ESA member states. As the two major contributors were Spain and Belgium. Additionally, Belgium, through the CSL Institute, is the country that has provided the coronagraph. The organization of the mission, CENER has led, and we were the system architect, and also providing some critical elements of the mission. But we were supported, very well supported, by a core team made up of 4 companies. Airbus providing the platforms and being responsible for the environmental testing. Redwire provided us most of the avionics and has led together with us the operations. GMB has been responsible for the algorithms of the formation flying, and finally Spacebell has developed the software of both platforms, both satellites, and also in ground. I would like to stress also that, as I said, there are 14 ESA members. Some of these countries, as you can see in the image and in the list, are the most recently countries entered in ESA. And we also had a number of SMEs and even startups. Some of them was the very first time that participated in a flight in a space program. Okay. Well, you see here the two satellites. We are talking about satellites is about 1 cubic meter in size. To give you an indication, both together the mass is 550 kilos. In the right side, you can see in the bottom right, you can see the coronagraph. You can see the occulter. You can see that big ring, 1.4 meters, which makes the occultation of the sun. And is where you have the fine propulsion system, 10 millinewton propulsion system. Because this satellite is responsible to maintain the formation. The coronagraph in the left is where we call it the coronagraph because it's the satellite containing the instruments. Okay, and there are additionally to the ASPIX instrument, the coronagraph, we have a couple of other instruments. We have in the coronagraph an electron spectrometer, which is going to measure the flux of electrons. And in the occulter, we have the data payload, is an instrument that will measure the total energy coming out of the sun, what we call the irradiance. Additionally, apart from making a number of maneuvers to test formation, we also will perform an additional experiment, which is what we call a non-cooperative rendezvous, which is going to be also important to develop technologies for the future for in-orbit operations. And then the most important for the formation flying point of view is the metrology units that we'll see now, which are located also in the occulter. Now you see here the two main instruments. One is the visual-based system, which is a camera that searches or looks for flashing LEDs which are in the other satellites, and that is the reference it uses to make the acquisition, which is, let's say, the coarse acquisition of the two satellites. But then when we need to achieve the tight formation, we make use of FLLS, which is a laser metrology system. This laser sends laser signal, which is retro-reflected, and then that provides a 3D error signal, which allows us to compensate both the distance and the lateral deviations from the direction we want to point. Once we are in the science mode and we are making use of the coronagraph, then we make use of an additional sensor. It's called the shadow position sensor. You see it in the bottom. And in that white round window that you see over there, if everything is perfectly aligned, then the shadow is cast exactly on that round window. But if there is any deviation from that, there are 4 sensors that you see in the picture that will detect the increase in the light, and that we use additionally that signal to correct the position if required. So basically, these 3 sensors are the metrology sensors we use to provide the tight formation flight. And then I leave the floor to the scientist, Mr. Sender, that will explain the experiment and the science we're doing in this mission. Thank you.
Thank you, Diego. So my name is Joe Zender. I'm the project scientist for Proba-3. So I'm from the Science Directorate, but located at the Technology Center of ESA in Noordwijk in the Netherlands. So as scientists, we are very happy to take the opportunity offered by the technology demonstration to address a very interesting and challenging aspect of solar science, which is the inner solar corona. So there are many processes of interest which happening in this close origin of the sun, let's say between the solar surface and the distance of 2 to 3 solar radii away radially out from the sun. Typically, scientists travel all over the world to observe this region during the total solar eclipses. So thus, we have good observations for this. However, only for 3 to 5 minutes once a year. We do this observation since already 300 years, and maybe it's interesting to mention that Edmund Halley was the first one to predict the location and the time accurately of a solar eclipse. So since this time, actually, we're going all out over the world to obtain these images. With the possibility of Proba-3 and the coronagraph aspects, we will not only increase the total amount of time where we get images, but an observation window will also have 6 hours. So instead of traveling, for example, you see on the left image on the slide, but also in my background here, you see an image obtained from one of our collaborators this year in April from Mexico. So we're traveling over the world for 3 to 5 minutes. And on Proba-3, we expect to get an average about 10 to 12 hours every week from the beginning of next year onwards. So we really appreciate this a lot. It will provide us a lot of information on the details and complexity of the solar corona and the events that is happening there. You can see in the image on the top left, but also on the right side, that it's a complex structure which is starting at the solar surface and is reaching out. And in this structure, so you see a two-dimensional image, of course, of a three-dimensional physical events happening there. But in this inner region, the coronal mass ejection, the CMEs, how we call them, they are initiated in this region. Because it's so difficult to observe the region, we hope to get a very close insight into this initiation process. The same is true for the solar wind. So the solar wind is originating, of course, from the sun, but it's starting with a low velocity and it's accelerated to what we call a slow solar wind or fast solar wind. And let's say if I'm speaking slow, fast, we speak about several hundred kilometers a second. So this has an impact not only on the Earth, but of course all of the satellites which are orbiting the Earth. So with this, we hope to get a better understanding of the initiation of this physical phenomena, to model them better and help to understand better the physics, but also the effect on satellites and on the Earth. So there's probably much more to say about the science, but maybe I'm leaving now room for questions to come. I guess that we are all happy to answer. Probably have to pass back to Emmett, right?
Thank you very much. So thank you very much to our participants for their explanations about this wonderful mission. As Joe mentioned, we now open the floor for any questions you may have. If when asking the question, first, if you could raise your hand on the Teams thing, so I know. Thank you. Oh, that was very quick. If you could raise your hands, and then when you ask your question, if you could just state your name and your affiliation, and then we will start. So I see it's Ian Sample. You are first up.
Hi everyone. Thanks so much for doing this. I think my question is probably for Joe. It would be good to hear what if you could just unpack a little bit more about how, if you can understand more about this region of the sun, and you talked about the solar wind, you talked about CMEs, if you can understand more about that, what kinds of applications or benefits might there be for the kinds of systems you're talking about, satellites you're talking about, the effects on Earth? I could just do with a bit more to help me explain to readers what the benefits of learning these things might be. Thanks.
Thanks, Ein. Let me first say, of course, we are from a scientific point first interested in to understand the physics, right? Where we have large gaps to understand. But you are asking about the application. So right now, if we want to predict the solar wind around our spacecraft, right? Let's say, and not only actually around the Earth, but for example, we have the agency has spacecrafts in near all of the planets in the solar system, more or less. To predict this properly, we need to model the solar wind starting from the solar corona, or from even the interior of the sun. We have these models, but these models are at the time being not able really to predict, for example, the initiation of a CME. So first we have to see the CME right now that is going to happen with the spacecraft. And from this point onwards, we then can feed our models to predict when would the CME, or when would the energy of a flare, or when would we cross actually between fast solar wind and slow solar wind, when would we cross these kind of boundaries. So the idea behind is, with the better understanding of the physics, we can also improve our modeling. And with the improvement of the modeling, we can then improve, for example, predictions for our satellites, and also, let's say, impact on the Earth itself, right? There could be also impact on ground-based energy centrals and so on, or on airplanes and so on, to improve this prediction.
Okay, thanks very much.
Thank you. Next I'll pass over to, is it Theresa Palm?
Yes, thank you. This is Theresa Palm from Süddeutsche Zeitung. I have a question that falls in line perfectly with your last answer, Joe. I'm wondering about the predictions of solar eruptions. From what I understand, they cannot be predicted at the moment. This is what we had with the polar lights in May in Europe. So can you expand a little bit on how this will improve the ability to predict solar bursts? And also, I'm wondering if you said the data taking is going to start in the beginning of 2025. Is that going to be in time for the solar activity maximum that is to be expected in the year? So are we going to benefit from the predictions that you are hoping to make?
I'm afraid I have to disappoint you. Don't expect that we do the first observations and that the improvement of the models are done the day afterwards, right? This is all very, very complex. This will take, I don't know, any prediction I'm doing is wrong, right? This is taking time. It will take a lot of scientists, a lot of modelers, a lot of engineers working together, also combining data from other instruments. And you have to see the interest in Proba-3 is around the whole world, but it's a common effort, right? With all of the spacecraft. We have a solar orbiter from ESA. We have the Parker Solar Probe from the US. The US are launching a few other small missions like Punch, for example. We have missions from India, Japan. So we all work together actually to solve the problem. But I have to disappoint you. It's very good that we get the data during, let's say, the high solar activity, but you have to wait a few years, right, before we really come up and improve the modeling and better understand this. This is not an activity which goes overnight.
Can I just add a follow-up question? Because you said you're going to improve the models. Those are not prediction models, right? They are models of how the physical processes play out in the corona, or which models are you speaking of?
Yeah, let's say so we have currently models to predict the evolution of the solar wind, right? If we have an observable in the corona, then we can predict the traveling through the solar wind. We have a reasonably good understanding of this, but we cannot really predict when the events are going to happen. So these models, which model the basic, let's say, model the magnetic behavior on the solar surface, we have to understand better what is the physics there and then put this into proper modeling. And then hopefully we have, let's say, I say hopefully, right? I cannot guarantee, hopefully we have the chance that these models can give us, at least statistically, the prediction of CMEs, flares, and probably other physical phenomena on the solar surface.
Great, thank you. So Dan, you're up.
Perfect, thank you. Thank you. Next question is from Dan Clary. Dan, can you? Oh, good.
Yeah, sorry, I couldn't unmute. Yeah, hello, this is Dan Cleary from Science Magazine. Thank you, everyone. I just want to ask two things. First of all, what is the timeline after launch? You know, how long before we see a first image? And once science operations have started, how long is the predicted length of the mission? And secondly, I wanted to ask, why is an external occulter better than an internal coronagraph in terms of image quality? Thanks.
I think I can take the first question. Maybe the second one, I don't know, we see Joe. But for the first one, so the timeline, the launch will be next week. We launched the two spacecraft attached together, and we will start the commissioning in this configuration. There are a lot of things we can already do, even when the spacecraft are attached, a lot of equipment to check out in orbit. If everything goes well, we expect to separate the two spacecraft from each other beginning of next year. And then there will be commissioning to do. We have a lot of functionalities to exercise in orbit. The two spacecraft will be drifting from each other after separation. We need to command some maneuvers to stop this drift, to put the two spacecraft on a relative safe orbit, and then to start little by little to test the metrology equipment that Diego described, and to activate the software functionalities to do the formation flying. So if everything goes well, maybe in March, we would have the first image. So when you ask a first image, implicitly, I understand the first image of the corona. There will be plenty of image before taken from the different camera of the spacecraft. But in terms of image of the corona, so we hope, but it might take a bit longer. This is a bit of an experimental nature, this mission. So we will have to see how the system behaves exactly in orbit. We have different ways to achieve what we want to achieve. We expect at best 3 months, and maybe it will take a bit longer. And then just to complete the answer on this question, then afterwards. So when we will start the operation and the scientific use of the mission, then we have enough propellant or fuel for 2 years of mission of formation flying. For the second question, Joe, do you want to answer?
I can go through it. So I'm very happy to give you a whole bunch of formulas now, but then you will not be happy with me. So let me try to give you to give you an image, right? To help you to explain this. Let's assume there is a clear sky outside in the night, and you have a walk, and you want to look at the star. You're standing in front of a street lamp, right? And the star is somewhere behind. If you put your fist up and you block the light of the street lamp, right, you don't see the light anymore. you still cannot see any star, right? Because the light that is spilling over your fist, over your hand, what we call stray light, this light is still so strong that it's much, much stronger and more intensive than any light from the stars behind. So if you now walk away from the street lamp, right? Let's assume you were 5 meters, you go to 10, 15, 20, 30, 50 meters, the street light is getting further and further away from you, and then you might need a smaller fist, right, and to block the light, and at one point you will see the stars. And the further you go away from the street lamp, actually, the more you will see the stars. It's a kind of an image. Physically, it's not correct, but it's a kind of an image to explain you why, if you increase the distance from the eye to the occulter, why the stray light that is spilling over the occulter is getting less and less. And basically, this is what we're doing. And then there is another point, actually, that still the stray light is disturbing our signal strength. So we are not saying we're flying a camera, we're flying a coronagraph. In the optical axis of the coronagraph, there is another occulter, a very small one. I think the diameter is 3 or 4 millimeters, something like this. And this little internal occulter is also reflecting this spilling over stray light out again of the optical path. So basically we have two occulters. We have the very far external occulter to reduce the first stray light, and then we have internally again another occulter which is reflecting even more. And then we hope we get a very clear signal, very comparable what you see in my background here, obtained during a total solar eclipse on ground.
That's great. Many thanks.
If I may, a comment and to complement the answer to the first question, to recall that after the 2 years of the mission and before 5 years, both satellites eventually will start decaying in the orbit and enter into the atmosphere to avoid debris for the future. And that will happen before 5 years. Is that right, no, Damien?
That's absolutely correct. Yes, 5 years after launch.
Okay.
Thank you. That's very good to know. I'm taking questions in the order they come. So actually, I have a written question from Kaya Burgess from the Times. And the question is, has ESA sought any advice from air squadrons who do formation flying on Earth? Could the UK's Red Arrows offer any tips? For example, what would be relevant for formation flying in orbit? So is there a link between display squadrons and what we're doing with Proba-3?
I think it was more an illustration, but we didn't have a direct contact with them. But I think we would be happy to exchange on what it takes to do formation flying, either on ground or in space.
That's good. Thank you very much. And I have another question in the room that's from MP Silath. I'll pass you across the floor if you'd like to unmute your mic and ask your question.
Hello, my name is Siddharth. I'm a journalist logging in from India. Thank you for giving me this opportunity. So first question, I have a couple. I'll go one by one, please. Why 600 into 60,000 kilometer orbit? Could you just mention why specifically this orbit, and why not a circular orbit? Because every time you go from 600 to 60,000, don't you have to spend more fuel to again come back in formation?
I can take this one. It's a good question. It's a limitation on the launch capacity. So it's true that it just in terms of pure formation flying for coronagraphy, we could be in the Lagrangian point on L1 or L5, or we could be on a circular orbit at a very high altitude. Why do we want to be at a very high altitude? Because we want to be as far as possible from the Earth, to have less gravity, not to have any perturbation, atmospheric drag, the magnetic field from the Earth. All these are perturbation for us. But to go on such orbits, we would need a launch capacity that is an order of magnitude more than what we could have with the launcher we can afford. So we remain a technology demonstration mission. We want to demonstrate something very ambitious, but with a reasonable budget. So that would be beyond what we could afford. So we selected this orbit, which is a compromise where we go high, 60,000 kilometers, to have this good environment to do formation flying. But then when we approach the perigee, indeed, we would consume more propellant. We could maintain the formation also over the perigee, but then we would consume a lot of propellant. So that's why we break the formation. They just free fly. But overall, we also consume propellant when we do the formation flying. So overall, this is the good compromise for what we want to achieve.
So thank you for that. My second question is, what would be the future applications of precision formation flying? Because this is the first of its kind mission of such magnitude and precision, if I may. So what would be the future applications? What do you foresee after the success of Proba-3?
Okay, maybe I can answer some. I'm sure that from the scientists will come many ideas. During the time we were performing the mission, we were addressed by many scientists because they can imagine many experiments where they need to separate two elements that need at the same time maintain the relative position very, very tight. I'll give you some examples. Imagine you want to do interferometry. Today, with the precisions we can achieve, this can be made obviously in the radio wavelengths. Unfortunately, we cannot go up as they would like to, for example, infrared. But we can do it now, and that will allow to make, for example, observations of two antennas looking in the same direction and having a base reference with a very constant distance. This is a good example. Or in the case of X-ray, you can have on one side a ring deflecting the rays, and on the other side having the detector separated both, 20 meters. This cannot be achieved with this technology. In the end, the problem we have is that there is a limitation on how large the satellites we can put in the upper stage of a launch. That's clear. And in the future, when we need, and as I mentioned, in the cases where we need to maintain the relative position of several elements, the only possibility is then formation flying. In this case, they were as if there was a kind of virtual structure maintaining together these elements. This is the first step in that direction. Obviously, in the future, we will be able to increase the precision that we can maintain between the elements, and that will provide obviously the possibility to do additional science. As I said, today in the area where I imagine that most will benefit is definitely science and Earth observation. And but we need to do this kind of missions to prove the technology first.
So finally,
I can also just in order so that I say something as well. So I think Diego is fully right. Particularly, there's quite some interesting spectrum of applications when you look into increasing the antenna size for very low frequencies. Sometimes you can actually build an antenna that looks very far into the universe for lower frequencies by not having this as one singular antenna, but have a pattern of antennas or satellites flying next to each other. That would be one typical example. And then, of course, if you get the accuracy even higher, than what we achieve here. There's other applications also in higher frequencies up to the optical domain, where you can think of creating very large and very, very powerful and performing instruments out of constellations of satellites.
Yeah, final question, please. So this is regarding the disposal of the satellites. I remember hearing that the satellites will re-enter the Earth's atmosphere maybe in 5 years from now. So particularly when we are in a 600 into 60,000 orbit, isn't it safer to push both the satellites far away from Earth while at 60,000 than bring it to the crowded 600 region and then bring it to the atmosphere to burn up?
I can take this one. Actually, why do we re-enter into the atmosphere? I think this is what I should explain. So we launch on an orbit that is 60,000 kilometer apogee, 600 kilometer perigee. But this is the orbit at the start of the mission. Then we have some orbital perturbation that are creating some force that over time are quite significant, significative, and that change the shape of the orbit much more than actually what we could do with the propulsion of the spacecraft. And these perturbations are the gravity from the moon and the sun. So these are the perturbations that slowly change the shape of the orbit, and we will actually, at the start of the mission, the perigee altitude will increase to up to 1,000 kilometers, and then the perigee altitude will decay up to a level where, because of the atmospheric drag, the spacecraft will re-enter. So it's really a natural change of the orbit, and for us to actively change significantly the orbit, as you said, to have an apogee even further higher. This would require a propulsion capability that we don't have. We would need hundreds of kilos of. So the atmospheric re-entry we have is due to a natural change of the orbit due to the perturbation, and so we are sure that we will re-enter after 5 years if we are injected on the correct orbit. This is just the natural effect of gravity.
Thank you so much.
Perfect. Thank you so much. I have one question. Pierre, do you want to ask the question yourself? Would you want me to read it for you? Well, I'll read it. So it's so from Pierre Senelier from AFP. Thank you. What are the prospects of using the precise formation flying technologies for satellite servicing?
I will answer that. Well, taking the advantage that we have two satellites, we can simulate different situations. And one of them that will be needed probably in the future is that when you have, imagine a satellite or some debris you want to remove and you want to approach, but obviously it will not cooperate because it's passive. This is what we are emulating with the experiment we are doing, this non-cooperative rendezvous. But again, a similar situation you may have when you need to service a satellite which has some malfunction, and eventually with some robot arm or something similar, you want to change elements. All this in-orbit servicing requires precise approach, and you have to do a number of maneuvers which are, let me say, delicate. Formation flying we will with this experiment, as I said, will let us know and learn what are the problems you may find when you are doing this kind of operations.
And if I may say, so just as we have on Proba-3, it's the part about the in-orbit demonstration. So we can also use this and the specific orbits that we are having here right now to exactly simulate and emulate a situation that you might have where we have an uncooperative satellite. Of course, we have both satellites under control, but we can exactly test these kind of maneuvers that Diego was just describing in order to learn also how we can approach an uncooperative satellite to remove it from debris from the orbits or for repair or whatever is the servicing aspect to that. So this is the part of the real demonstration. Then, of course, we might, for this maneuver, lose one orbit where we cannot have the scientific results, but we learn from that. And that's clearly one part of what I'm really trying to emphasize. It's not only this fantastic scientific research that we can do here and improve, but it's also the testing part. It's the Proba part of the name.
Thank you, Dietmar. If Taylor allows me, if we have time for one last question from Ludwig Jovanovic. It's a quick question, then we can handle it. Ludwig?
It's a quick question. Hello, Ludwig Jovanovic for Rheinische Post from Germany. You're launching with an Indian rocket, as far as I know. And is there a specific reason because there was no European rocket available at the time, or are there any other reasons? Thank you.
Maybe I take this one as also before Damien was explaining the specificity of the orbit. There is a compromise. In the orbit itself, we cannot afford to have a very large launcher, very powerful launcher to go to an orbital far out orbit. And the same is basically here the case. The two possibilities in Europe are not exactly fitting to the requirements for this specific mission, for this now economically right orbit here. So since we are anyway cooperating, of course, and exploring all possibilities, we choose the most economical solution here with our excellent partners from India.
That's lovely. Thank you very much, Dietmar. With that, I think we've covered all the questions from our audience. Just leaves me to thank both our speakers and also the participants for spending the time with us this last hour to learn a little bit more or a lot more about Proba-3. So thank you so much, everybody, and have a very good afternoon. Thank you.
Thanks a lot.
Thank you, everyone.
Goodbye.
Thanks, everyone. Cheers.
Bye. Bye. Bye.